All right. Time to continue with section 1.8. Let's do another example here. All right, let's do f of x is equal to x squared minus 7 divided by x plus 2 at x is equal to 1. What is m? Well, again, f of 1 plus alpha minus f of 1 over alpha is what our m is. So this is going to be 1 plus alpha squared minus 7 all over 1 plus alpha plus 2 minus 1 squared minus 7 all over 1 plus 2. Everything divided by alpha. Okay. So this is going to be 1 plus 2 alpha plus alpha squared minus 7 all over 3 plus alpha minus 1 minus 7 all over 3. Everything over alpha. So then over here, we get a negative 6 plus 2 alpha plus alpha squared, everything divided by 3 plus alpha, minus a negative 6 divided by 3, everything divided by alpha. Notice that this is the same thing as a negative 2, and the negatives cancel to give me a plus 2 over here. And notice that over here we get alpha squared plus 2 alpha minus 6 divided by 3 plus alpha. Everything divided by alpha. Okay, this is divided by 1, so we can multiply top and bottom by a fancy number 1. Call it 3 plus alpha to give them a common denominator. So we get alpha squared plus 2 alpha minus 6 plus 2 times the quantity 3 plus alpha. Everything divided by 3 plus alpha. All divided by alpha. Then we can allow this 2 to go through here and multiply by reciprocals here. So we get alpha squared plus 2 alpha minus 6 plus 6 plus 2 alpha all over 3 plus an alpha times 1 over alpha, because when we multiply by reciprocals. So this becomes, in the denominator, alpha times the quantity alpha plus 3. Up here, the 6's cancel. Oh, and you guys are not on here. 6's cancel, and the 2 alphas combine. So we get alpha squared plus 4 alpha. Okay. And we can factor out alpha from the numerator. We get alpha plus 4 all over alpha times the quantity, alpha plus 3. We can cancel out alpha, so we get alpha plus 4 over alpha plus 3. Notice that this renders the real result, 4 over 3. So this is our slope. This is the slope of the tangent line of the function x squared minus 7 divided by x plus 2 at x equals 1. All right, so let's do another example. What if our function is equal to the square root of 3x plus 1 at x equals 2? What is the tangent line? Well, the slope is f of 2 plus alpha minus f of 2 all over alpha. This is equal to the square root of 3 times 2 plus alpha plus 1 minus the square root of 3 times 2 plus 1, everything divided by alpha. This is equal to the square root of 6 plus 3 alpha plus 1 minus the square root of 6 plus 1 all over alpha. This is equal to the square root of 7 plus 3 alpha minus the square root of 7 all over alpha. Do not approximate this to be the square root of 7 minus square root of 7, because you know that that violates the approximation principle. So what we're going to have to do is multiply top and bottom by the radical conjugate. So what this is going to be is the square root of 7 plus 3 alpha minus square root of 7 all over alpha, multiply top and bottom by the radical conjugate. So what do we get in the numerator? We get 7 plus 3 alpha minus a 7. And in the denominator, we get alpha times the quantity square root of 7 plus 3 alpha plus square root of 7. All right, these 7s up here cancel. So we get 3 alpha times the quantity alpha times the square root of 7 plus 3 alpha plus a 7. Alphas cancel, so you get 3 divided by the square root of 7 plus 3 alpha plus a 7, which approximates to 3 divided by the square root of 7. Oh, and this needs a square root on it. Plus square root of 7. So this becomes 3 all over 2 root 7. And we can rationalize the denominator, multiply top and bottom by fancy number 1. So we get 3 root 7 all over 2 times 7, which is equal to 3 root 7 all over 14. So this is our slope m. And then y minus y1 is equal to m times x minus x1. Implies we got y minus, what is our x and y? Well, first let's figure that out before I jump. So x is x1, y1 is the same thing as 2 f of 2. Let's figure out what is f of 2. Well, that's square root of 3 times 2 plus 1. That's square root of 6 plus 1. That's root 7. So this is going to be the same thing as 2 root 7. So then y2 minus y1. So then y minus y1 is equal to m times the quantity x minus x1 gives us y minus root 7 is equal to the slope that we've discovered, this 3 root 7 all over 14 times the quantity x minus 2. Moving the calculation to another page here, allowing you to see what that calculation is real quick. Moving this calculation to another page. What we get is y minus square root of 7 is equal to 3 root 7 all over 14x minus 14 is really 2 times 7. So then this becomes 3 square root of 7 all over 7. So then when we add a root 7 to both sides, we get y is equal to 3 root 7 all over 14 minus 3 root 7 all over 7 plus a square root of 7. Okay. So then that implies we get y is equal to 3 root 7 all over 14x minus 3 root 7 plus multiplying top and bottom here by 7 root 7. This is going to be all over 7, and this is going to be all over 7. Okay, so because they're under the same denominator, we can add them. So 3 root 7 plus 7 root 7 is the same thing as 4 root 7, positive 4 root 7. So it implies we get y is equal to 3 root 7 all over 14 x plus 4 root 7 all over 7. Okay, so that's the equation of the tangent line. This is the equation of the tangent line to that function. All right, so now that we have ample practice on doing this process, let's get to the more subtle reasons as to why this is so important. All right, let's do this via an example. Let's say at 2:11 p.m., a car enters mile marker 83, and at 3:26 p.m., a car enters mile marker, let's say 172. What was the car's speed during to 11 p.m. to the interval 2:26 p.m.? The answer is you can't determine what the car's speed was at any given time, you know. You can only determine what the car's average speed was to have traversed that distance, right? You only know that the car traveled this much distance in this much time, but you don't know how fast it was going at any minute during 2:11 p.m. to 3:26 p.m. That information is not accessible to us. We don't know what the instantaneous speed of the car was at, let's say, 3:15 p.m. or at 2:45 p.m. We can only calculate the average speed, and that's equal to the distance that it traveled divided by the time that it took. So that's 172 minus 83 in miles divided by your 3:26 p.m. minus your 2:11 p.m. in minutes. All right. So this ends up giving us 89 miles per 75 minutes. And let's say we want it in miles per hour. So we do a conversion that in 60 minutes, we have 1 hour. Okay. So that implies that this gives us an approximate average speed of 71.2 miles per hour. This is the average speed. Notice that that's the only thing we can claim. We can't say that, oh, at 3:05 p.m., it was going 20 miles per hour, but at 2:36 p.m., it was going 120 miles per hour. You can't say that. All you can say is that the average speed it had must have been 71.2 miles per hour, because one of the ways in which it could have traversed that distance is if it stayed at 71.2 miles per hour and it just stayed at that speed. It didn't slow down, it didn't speed up. Well, we all know that that's not the case. Cars don't just stay at 71.2 miles per hour. They fluctuate. They go a little faster, they go a little slower. There could be wind, there could be traffic, there could be someone coming into your lane. So we know that this is not accurate. We know that this is the average speed, but it's a very crude piece of information. With the invention of hyperreal numbers, we can actually figure out what is its speed at any second we want. That is, what was its speed at 3:08 p.m.? We could figure that out. Now, one thing we do need to know is what is the function that models its speed. And then another thing is that we need that function to be continuous, which it most likely will be. And then after that, we can use calculus to find the instantaneous speed. I will make a note that if this has a positive sign on it, notice if we switch these guys, it would have a negative sign on it. That's due to the fact that when you get calculations that involves speed and you don't specify direction, then the positive can be thought of as one direction, and the minus can be thought of as the opposite of the direction you picked. So if this was 71.2 miles per hour north, then automatically the negative would be 71.2 miles per hour south, which is south is the diametric opposite of north. So keep that in mind. If you've had trigonometry and you ended up discussing vectors, you know that a vector is a quantity that has magnitude and direction, and this is the difference between a vector and a scalar. Okay, so in general, average velocity, or just the average period of a function, is equal to the function f of b minus f of a all over b minus a. All right, for f of x. That would give you the average of the function, or the average speed if it's quantifying the speed, if you will. It just depends on what is f of x quantifying. So let's do another example. Given an electron, symbolize it with E minus, say that it's traveling in an electromagnetic field. And since we know that electrons in an electromagnetic field will be moving, and let's say its function, its position function as a function of time, p of t, is given by the equation t squared plus 2t plus 1, and this is in meters. Okay. Its position as a function of t, where t is equal to seconds, or time. P of t is in meters, or distance. Okay, what is the electron's average velocity? Well, I can't just say what is its average velocity, because we have to say what is this average velocity between a time interval. When we ask that question, we say between the time interval, let's pick between t equals second 1 and t equals second 3. Well, we use this equation right here. So f of 3, or actually in this case p of 3 minus p of 1 all over 3 minus 1. This is equal to 3 squared plus 2 times 3 plus 1 minus the quantity 1 squared plus 2 times 1 plus 1 all over 2, which is equal to 9 plus 6 plus 1 minus the quantity 1 plus 2 plus 1 all over 2. This ends up becoming a 4. Okay, so minus 4. So this becomes, these two combine to give me 10. This is 16 minus a 4 all over 2. This is a 12 all over 2, which is the same thing as a 6. Aha! So the average velocity is going to be 6 meters per second between second 1 and second 2. That's the average velocity. What is the instantaneous velocity? Yeah, you heard me. What is the instantaneous velocity? Well, At what time? Well, let's say at time equals 1 second. What is the instantaneous velocity of the electron? Well, I haven't told you how to find instantaneous velocity, although we've already discussed the idea. It all boils down to the slope of the tangent line, because the slope quantifies the rate of change of the function. And so what we need to find is what is the slope of the tangent line at t equals 1 of p of t is equal to t squared plus 2t plus 1, because this function quantifies the motion of the electron in the electromagnetic field. So what we want to do is say, what is the instantaneous velocity? Well, that's the same thing as the slope at 1, p of 1, but that's 1 comma 2, or 1 squared plus 2 times 1 plus 1. So that's 1 comma 1 plus 2 plus 1, and that's the same thing as 1 comma 4. Okay, so this is the same thing as asking what is the slope of the tangent line of the function p of t at 1 comma 4. Okay, so to find m, we have to say what is f of alpha plus k minus f of k all over alpha. But that implies m is equal to f of alpha plus our k is equal to 1 minus a f of 1 over alpha. And we're not even talking about f, we're talking about a p. So this is f of p plus alpha, f of alpha plus, or p of alpha plus 1 minus p of 1 all over alpha. This implies we get alpha plus 1 squared plus 2 times alpha plus 1 minus 1 squared plus 2 times 1 plus 1, everything over alpha. Notice that this reduces to alpha squared plus 2 alpha plus 1 plus 2 alpha plus 2 plus 1 minus the quantity 1 plus 2 plus 1 becomes a 4 all over alpha. So this becomes alpha squared plus 4 alpha plus 4 minus a 4 all over alpha. 4's cancel. Moving the calculation up here, you get that this is alpha times the quantity alpha plus 4 all over alpha. Canceling out the alphas, we get this is the same thing as alpha plus 4, which renders the real result 4. Wow. So the instantaneous velocity of the electron at the time equals 1 second inside the electromagnetic field is 4 meters per second. Whereas its average between 1 second and 3 seconds was 6 meters per second. So clearly the electromagnetic field must have sped it up. All right. It must have sped the electron up for the average to output that value. So, instantaneous velocity. V of t is equal to p of t plus alpha minus p of t all over alpha, where p of t is the position function. Notice that this equals your slope. So v of t is a slope. It's an equation that for every input of time, it outputs the slope, which is the rate of change of the position, because velocity is the rate of change of position. Just like the fact that acceleration is the rate of change of velocity. All right. Here's another example. Let's say an electron neutrino is being emitted from the core of the sun, and it's traveling towards the Earth with a position function p of t squared. What is the electron neutrino's velocity at t equals 2? And when we say what is its velocity at t equals 2, not from t equals 2 to some other t equals another time, this is implying it's the instantaneous velocity at t equals 2. All right, because average velocity takes 2 time inputs and 2 positions and finds their difference and then takes the ratio of that. But the instantaneous rate of change of position, which is velocity at time equals 2, is quantifying just how fast is it moving t equals 2 seconds after being ejected out of the core of the sun. Okay, so then that's v of t in general is equal to p of t plus alpha minus p of t all over alpha. But at t equals 2, this is v of 2, so this is p of 2 plus alpha minus p of 2 all over alpha. And this is 2 plus alpha quantity squared minus 2 squared all over alpha. And this is 4 plus 4 alpha plus alpha squared minus 4 all over alpha. Cancel out the 4's. This is alpha, factoring out alpha plus 4 all over alpha. Cancel out alphas, we get alpha plus 4, which renders the real result 4. So we get 4. I didn't tell you what this was. I could say that this is kilokilometers per second. Or I could say that it's miles per second. I'm inventing this problem, so I can call it whatever. Let's say it's going miles per second. Can you imagine how fast this electron neutrino is moving? If it's moving 4 miles per second, okay, that's very fast. That means in 10 seconds, it's moved 40 miles. So that is going very fast. Talking about car velocities that go 40 miles per hour. This thing can go 40 miles in 10 seconds. So that's a really fast moving particle. Electron neutrinos can approach very fast speeds because they have very little mass. Their mass is approximately almost 0, but non-zero. So that's why they can move so fast. Okay. Let's do another example. Let's say Bitcoin stock value is given by the equation f of t is equal to pi t squared minus 3, where f of t is in dollars and t is equal to days, where, you know, t equals 0 is today and t equals 1 is tomorrow and t equals 2 is the day after that, yada yada yada. You get it. So here's a question. How fast is the price changing in 30 days compared to now? That is the average rate of change. So that question is 30, f of 30 minus f of now, all over 30 minus now. So that's basically, that's pi 30 squared minus 3 minus pi times 0 squared minus 3, all over 30 So this is the same thing as pi 30 squared minus 3. This becomes just 0 and plus a 3 all over 30. 3's cancel. So we get pi times 30 squared all over 30. Cancel this out. So this is 30 times pi, which approximates to, when you plug it into your calculator, to $94.14 per day. So yeah, that stock is going up. It's increasing very rapidly. So that is the average rate of change of the velocity. But what is the instantaneous rate? Did I say velocity? I'm at stock value. So what is the instantaneous rate of change of the stock? Okay, that's now what we want to know. So let's say, I don't know, at a day 30, the instantaneous rate of change at day 30 would be your f of 30 plus some alpha minus f of 30 all over alpha. So this is the same thing as 30 plus alpha times pi squared minus 3 minus pi times 30 minus 3 all over alpha. So this becomes pi times the quantity 30 squared plus 60 alpha plus alpha squared minus 3 minus your 30 pi plus 3 all over alpha. So this reduces to 30 squared pi plus 60 alpha pi plus pi alpha squared minus 3 pi minus 30 pi plus 3 all over alpha. This reduces to a negative 33 pi. Okay. And so you notice that anything with an alpha in the numerator will approximate to 0, right? So we then notice that through 30 squared pi plus 3 minus a 33 pi is all that will remain. Okay. See here, I think I made a calculation error. Yeah, I think I made a calculation error here. Let's start back up from here. So over here, this is going to end up equaling pi times 30 squared plus 60 pi alpha plus pi alpha squared minus 3 minus 30 squared pi plus 3 all over alpha. And quantities can cancel here. And this cancels this. So this gives me 60 pi alpha plus pi alpha squared all over alpha. Factoring out of alpha, we get 60 pi plus a pi alpha. Cancel out the alphas. Then we get 60 pi plus pi alpha. Notice this renders the real result 60 pi. And this is approximately $188.5 per day. So notice that the instantaneous rate of change versus the average rate of change are completely different. One elucidates that it's moving faster than expected because at that instant, it's moving $188.5 per day. In the positive, its value is going up. But on the average, we saw that, from t equals 0 to t equals 30 days, it was just 94.14. So as you can see, the two values are very different. Knowing the instantaneous rate of change versus the average rate of change give you two different pieces of information. One could argue that the instantaneous rate of change is a finer, more precise piece of data, whereas the average rate of change is a crude estimate. That allows us to finish up section 1.8. You guys now have all of the material for the first exam.